Okay, so I hope I'm audible. Shall we start then? Shall we start? Okay, so can someone give me a feedback? Okay, fine. Hmm, fine. So I'll just share my screen. Okay, so last class I think you have seen that two lectures. So which was explaining controls, closed loop control, and you might have already second lecture explaining transfer function, right? So what do you seen in system we can represent using a input, output, and control, right? This can be basically defined as a control problem. We are trying to control a something, a physical phenomena, or even electrical, magnetic, or mechanical, hydraulic, or pneumatic thing, right? It's always a control problem. It may be speed, it may be temperature, it may be humidity, it can be anything. It can be electric parameter or electronic parameter like amplification factor, gain, etc. So a lot of things can be done, control using this control problem. So you have seen that there's an input and we are trying to control the output. So we have a system model. We can call system transfer function. We call it transfer function, right? Which connects the input and the output, right? So transfer function usually can be defined as the relation between input and output, right? We can this is a transfer function in generally, right? Although in order to define transfer function, we have to use a lot of Laplace transform and all those things for mathematically understanding the depth of the same thing. So right now, today in this class, we will move a bit further, not explaining again transfer function, but we'll explain transfer function again, maybe in after two lectures. So right now, we'll again just see what are the different models and how the block diagram modeling can be done, and how not exactly modeling. Let's see the models, the simplification of models, right? What are the different operations we can do on this block diagrams, etc. So after practicing a bit of those block diagram reduction, then we go deeper into Laplace transform, how we create a transfer function. For example, we have input to the motor, we have motors rotating, which is the output. So how to model a system using this transfer function? Okay, so here we'll try to reduce the models, block diagrams, right? So we'll discuss that thing today. I think in last lecture you might have seen uh, the author or the Brian maybe explaining how an input, say I have an input V, I have input V and I have two blocks. He was explaining D, the gain. This is say for example amplifier. Amplifier have a gain G, whatever, or K. So when the input travels to the amplifier, for example, it has a gain G. V is the input, and the output. What will be output? Output will be the input multiplied by the gain, right? This is the output, right? Say for example, you have two gain, two amplifier. For example, you can draw like this. This is the amplifier with a gain G1, and I have another amplifier with a gain G2, right? So we know I give an input, a small input V, it's a voltage, small voltage. So the first amplifier output will be G1 times the input voltage V, right? G1 times, this is G1, right? And what will be output of the G2 amplifier? The input to the G2 is G1 into V, G1 into V. Now the output will be G2 will be multiplied by to that amplified. G2 times will be amplified again, and the output will G2 G1 V. Right? So whenever two blocks or two gains are in series, we multiply them both. Right? This I think you are familiar with, because one of the block will have some kind of input output characteristics, and another block is kept in series with it, with another input output characteristics. So according to the block diagram reduction method, we can multiply these two blocks, right? So this I can combine together. This block, two blocks I can combine together to make a one block for simplicity. G1 into G2, right? Input will remaining same, the small input V, and the output will be the same thing, that is input times transfer function G1 G2, input times the gain, right? So this is an example of electron, example of amplifier. So likewise all system whenever two gains are in series, we can multiply them together, right? So I think another example you have taken last time is, say we have an input V, we have a block D, and for example G, another block G, and you have output, for example you have output Y, right? Now if we have a closed loop control system, we'll we'll have a sensor, definitely we'll have a sensor in the output, and the sensor will be feeding the output to another block, say I call it H. This is the feedback gain. You can say feedback gain, because this sensor is sensing the output and giving the output to this H block. And now this is again added to the input block. Right now we have option whether we can add to the input V or subtract to this. So I have another option here, another block here which can add or subtract. That means this block can say this is plus, this can be plus, and this can be also plus. That means the feedback I'm adding to the input, right? This is one option. Another option is I can, usually in the example we have discussed is we are subtracting. We are subtracting the feedback. Why we are subtracting? Because we need to know how much error. We are expecting some output and we want to know how much error is there in the output compared to the input. So we need the V is the input, and we are checking whether my output has been achieved the desired level. So what I'll do, I'll just use this to subtract my output. So this is going to the plus or minus. This is plus, this is going to minus, right? So what is the meaning of this? The feedback output, the feedback the output is going to gain H and is getting subtracted to the input before going to the D, gain D. So we can say this is the error function. This is error. What is the error? The difference between the input and the output. Okay, so what is our, ideally we have to reduce the error. Error should be zero ideally, right? So when error is zero, we can know that the output has achieved the desired state or desired output or desired level. Whenever there is an error, whenever there is an error, that means the output has not reached the desired level. Error can be positive or negative, right? Sometimes error is more than what we expect, so we call it positive error. Sometimes the output is less than what we expect, so we call it negative error. Okay, so here what I have done in last lecture, I think you have seen the first the simplification. We can multiply these two together, D into G, because they are in series, right? So what he has done, he has tried to simplify it by combining these blocks together. So he has done like this, and D into G is the overall transfer function. Now, what is Y here? Now we can write Y as in terms of input and gain. That is, now Y equal to error E into D into G, right? D into G, right? Because the signal passing through a transfer model or transfer function or block is multiplied by its gain. So E into D into G is my output Y. Now this Y is going to the H as a feedback. Now what is the output of this feedback loop? We have Y into H is the output of the feedback loop, right? Closed loop feedback. It's called H is called feedback gain. Okay, so Y into H is the output of the H block. Now, what is error? From this equation, we can error equal to the input minus y into H, right? Error equal to input V minus y, the feedback output multiplied by the feedback gain H into y minus H, right? Now substitute this value of y in this error equation, right? This equation, this is our error equation. Now let me substitute this. This is, let's make equation 1 on the top right. Let's substitute y here. Or let me substitute reverse. Let me substitute equation, error equation into 1, 2 into 1. Let's, I suppose 2 e equal to v minus yh is equation 2. Let me substitute this here. So what happens? So I will have something like that: y equal to error equal to v minus y into h times edg, right? So now y, there are two y's, we can combine these two y's together. So what will happen if we combine these two y's? So v equal to input, we had to get into terms, like some terms like input output by input, some kind of, so that we can get the transfer function. So right now I'm trying to simplify in my mind. Yh plus, we'll get yh plus y by edg, something like this, we'll get something like that, right? So edg comes to left, so y by edg in left, then v will be the y plus right. Can someone give me a comment? Is it right? I'm just trying to do fast. So let's see now. V equal to y common h plus 1 by edg. Yeah, someone. So what will happen?
Sir, we place in place of D. We put the value of E equals to V minus YH in place of E in equation 1.
Yeah. So
So Y equals to V minus YH into DG.
oh, sorry. E is not there. Fine. Got it. Fine. Okay. E is gone, right? So E is gone here. E should
Okay.
not be here. So will it solve it? Is it okay?
Yes, sir. It will become equal
Okay.
to V upon 1 upon H plus 1 upon DG.
Yeah. V equal to y into h plus 1 upon dg. Fine. Okay. Fine. So this is like this. So again, we can simplify y by v, output by input. What will get y by v? Y by v. Let me write this. Let me clear this. So we got v equal to y into 1 plus h by dg, right? Can someone tell me what was the relation we had? V into 1 by dg, h plus dg, right?
Sir,
Anyone?
yes, sir. H plus 1 upon DG.
Okay, h plus 1 upon dg, right? So we can simplify. We have to put the form output by input form. Output by input. That is equal. We'll get the transfer function, right? This is v1, output by input. Now we can say y by v. Y by v will be getting. Um, so let me simplify this initially. So v equal to y into dgh plus 1 divided by dg, right? So now y by v will get y divided by v, we will get dg divided by 1 plus d into g into h, right? So this is the uh, overall transfer function of the closed loop we are discussing. Dg divided by 1 plus dg. dg into h, right? You can see the feedback transfer function h or filler gain is coming in the bottom h. Okay, so what we have done, we have simplified the closed loop control system into a open loop single control system. So what is happening here, instead of having a closed loop, we have modified the plant, or the system, so that we can represent using a open loop system. So the same closed loop system, we were input is v and d into g, and this output is y and h. This is a closed loop system. Now we can represent this using an open loop like modeling. This is v, output is y, and the this is change, the transfer function is change dg over 1 plus dg into h. Okay, so what you have done, we have modified the plant actually. We have modified the process control. We have changed the process control problem and represented the closed loop using a open loop system. System is modified. That's it, right? So this kind of reduction, this kind of simplification of our system with a lot of gains, a lot of feedback paths, a lot of different channels, input and output, is called as block diagram reduction, right? So the block diagram indicates the process or the system. Now we are going to reduce it, right? Let's see what are the different ways. This is one way we have reduced the closed loop feedback into a open loop feedback. Now this is system is simplified, right? So in this class, we'll discuss a lot of simplification mechanisms so that we can practice a lot of mechanisms how to simplify a block diagram. Then we can move to the theoretical aspects of the transfer function. Okay, so let's suppose we'll take another example. So suppose I have a signal here. Say it is the signal I, right? Usually this is represented is, because we are always concerned about the Laplace transform, right? Or the Fourier transform, because it is easier to apply the uh, gain, right? Gain in control system, or sorry, in signal system, you have seen a system is represented using the s square plus s plus 1, s square plus something like that. So it's easier to multiply in Laplace transform, and your solution can be easily estimated, or stability can be understood using transfer function in Laplace transform. Okay, so let's see is input. Suppose I divide this is into different output. So here we should understand that each of these different divisions will always have the same input or same signal is, or I, whatever we can mention. Okay, so this is very important thing. So there is no like drop in an electric signal is traveling through a conductor. There's a drop, but here all the signal as its same polarity, same magnitude we are getting in the output. Now suppose I need to add another two signals. What I'll do, I can add one signal here. So let me add, I need to have a adder, right? I'm adding these two signals. So I adding this signal with another signal. So this is I into k. This is ks, right? So what happens now? The whole thing will be changing. Now ks will be added with all this signal is plus ks, is again plus ks. Okay. Now this is plus and minus. I can also do it minus also. This remains, this remains same. Plus or minus also. This remains plus or minus in the output also. Okay. So this is this block is called there's a name for this block. This block is called as summing block. Okay. So this is the summing block. This is one thing you have to remember. Summing block. Right? This can be plus or minus. Right? Usually we represent like this, a block and in a cross. So one input is coming here. If it is plus, I can write plus here because this is being added in the output. And there is coming feedback loop. It is minus. I can say minus here. Now the output is here, right? So this is x. This is y. The output is x minus y. Okay. So next important is after summing block, after the sharing block or the distribution point. Now we'll come to some reduction mechanism. So first thing we have seen the gain. Gain has to be multiplied together. So we have, say, we have input R going to a block G1 and the block G2. So your output is overall gain. You know G1 into G2 will be overall gain, and your output will be y equal to r times input into g1 into g2. You have seen, right? So the net result we can say simplified block diagram is g1 into g2, right? G1 g2, and output is r. So input is r, output is y. Okay. Now what about this? Suppose input is r, it is divided into two branches, and one is transfer function and transfer g1, and that is g2, right? And they are combined in the output using a summing block. So summing block I'll show like this. Block, this is plus, this is minus, this is plus. So what will be my output here? You can type so that I can see what will be the output here. You can see both are in parallel. You can see these two blocks G1 and G2 are in parallel. Okay, this is in parallel. Yeah, you can see parallel. So what will be output? Output by us is input into, right, G1. G1 is in add, this is addition. You can see this addition here. So G1 addition, and this is in minus. G2 is minus G2. So this is my output, right? So what is the net transfer function? We can see the output is r into y. Output y equal to r into g1 minus g2, right? So when you calculate output by input, we know, so this is y by r. So y by r, we can say this is the transfer function, and this is the transfer function. So transfer g1 minus it is net. So the net transfer function I can say is g1 minus g2. G1 minus G2. This is input R, output is Y, right? So these complicated parallel complications can be simplified into a single transfer function G1 minus G2. Now, if this was plus, if G2 was going to summing block as plus, same thing will happen here. G1 plus G2 will be coming in the output. Clear? So this is the way we reduce a complicated block diagram or transfer functions into a single transfer function for the simplicity, for analysis, for understanding the stability, etc. Okay. Now I'll give you small such things, and you can simplify it. Now, before that thing, I'll just for the clarity, we'll discuss that I have input A. Now I'm changing the variable A. Now I'm giving a gain G to this input. Now I have output. What is my output? A into G. A into G. Right? Now, sometimes I have to change the node point, branch point. It's called branching point. Now there was a branching point before the A is entering the block G or gain G. Right? So the variable A will be, and this point will have a signal A. Now suppose I want to move this node or this branching point to right side of the gain. That means I need to move this into right side. So what will happen? So I should know that when I move this node branch to right side of gain, so what will be signal? That is, this is the status. So what will be signal there? Initially you have A, output as A into G, A into G, right? So what will be change happen? Now the A here has become A into G. Now I need one more block here to compensate for the additional gain. So I need to divide to 1 by G, so that I'll get the signal A back, right? So what I have done here? So what I have done here? Both are same. Both of these block diagrams are same. The only difference is the branching point. The branching point in first case, is before the gain block, before the input is going to the gain, and the second, the branching point has taken right side or after the amplification or the gaining, giving the gain to the signal, right? So the output is remaining, the AG is remaining same, but I need a divider 1 by G, dividing the signal, so that I'll get the signal A back here also. Okay, so this you can say moving a branch point ahead of the block and behind a block. So what is the importance? You need to change the gain, right? The signals should remain the same. That is the only thing. Okay, so we have just moved the node point. Now, if I change the node point before the block, things will be remaining. Say here I'm having the input A and the gain G, and here AG, and again I put a output here AG. So both these branches are having the same signal. Now, if I need to put this branch left of the gain block, that means this I need to put it here. You can easily understand that what will be happen. We need to provide this G extra gain here, which was not there before the gain block. So the net resultant block diagram will be A gain. This will also remain same. Now this block has to be here on the left side of the gain block. So I need to provide another gain G, right? So that the both output are remaining same. A into G is the output here. Here also A into G will be the output on. Okay. So here what I have done, moving the node point to the before the gain point. This is node point. This is the node point. I'm moving this node point to the left, left of the block, left of the gain or transfer function block or the gain block. Okay. Now, now let's do the same thing with the summing point, right? So suppose I have a signal A. Suppose I have a signal A going to summing block in addition mode plus, right? Now again I have a input say B. It is always going as adder. A and B are going to summing point. So the output, it will be A plus B. Now I have a gain here, G, right? So here we have A plus B, and the output will have G into A plus B, right? This is my output. Now if I need to move the summing point ahead of the block, that means I need to move the summing block. This is my summing block ahead of the gain. I need to move the summing block somewhere here. So what will happen? You just need to focus on the output. Here we are getting output G into A plus B. So if I move the summing block ahead of the gain block, what will happen? I need to give the gain individually to both of the signals, right? I need to give the gain to A, and also I need to give the gain to B, both, right? Why? Because my output is G into A plus B. So what will happen? So your net simplified gain, not simplified, we can say the net resultant after moving the summing point after ahead of the block is like B going with the gain G. Also A is also going with the gain G. Again, these are getting into summing block. Summing block. This is also plus. This is also plus. Right now, the output is same. G into A plus B. So what you can say is slight difference. The only difference is the common gain. The common gain here. The common gain here is transformed to branch. Each branch, because it's taken left of the summing point, or summing point is taken right of the block. So we can see that the gain is distributed within the each branch separately. Okay. Logically, it is very simple, but you need to use this at appropriate time. Suppose you may not be able to reduce the complicated block diagram, so you have to use this moving the summing block after the gain block, or reverse moving the summing block to back of the gain block, etc. Okay, so you just need to refresh all those concepts. Same thing I should use when I am to move the summing point before the block. For example, I have a summing block here. This plus with two signals here. One is gain A with a gain G is entering the summing block, and there is B. Signal B is also entering the summing block. Now, what is my output? A into G, right? So this point we know signal is A into G going to the summing block, and here it is B. So my output is A into G plus B, right? Now the point is I need to move the summing block before the block. Now I need to move the summing block before the gain block here. So I need to keep the summing block here. So what will be the change? So you just see the output A into G plus B I need. So if I move the summing block before the gain block, right? That means after the gain block, I'll be getting the after the summing block, I'll getting the gain block like this. So what will be the change happen? Just see the output, we can understand. Just see the output A into G. So when A is coming, gain is fine. For signal A, I can give a gain. So definitely I can directly draw A. A can be directly moved to the summing block, right? But if B also directly moved to summing block, what happens? Yeah, your output becomes A plus B into G. A plus B into G, which is not equal to, yeah, G into A plus B. But this is not what we want because I need output A into G plus B. So I don't need this output. My output should be matching in both block diagrams, should be matching because both are same. I'm trying to simplify. So the output or transfer function should not change. So what should I do? Yeah, I need to add something here. I need to add something here. What should I add? B is going. I need to add a 1 by G here so that my output remains the same. Clear? So right now you can see if I add a 1 by G gain the transfer function at the top, my summing point will get the output B by G is going to the summing block, and here A is going. So what will I get? A plus B by G in the output of my summing block. Here A plus B by G. Now again it is going to the gain G. So again multiplied, the signal will be multiplied here G into A plus B I'll get in the output, which is same as my previous block diagram. Right? So what I had done in this example, I had tried to move the summing block before the gain block. The only thing is you need to make sure your outputs are same. Here A into G into A into G plus B is the output. Here also A into G plus B is the output in right top or bottom right. Right. So what I have done, I have done a attenuation or a de-amplification or reduction of the signal amplitude. Right. So that my output is same. Right. Okay. Now we have multiple signals. These things remain the same. Say for example, I have a signal like this, A and B plus minus A. Here I have the signal B. Now I have another summing block here. This signal is again subtracted with another signal C. C. So right now I can exchange or interchange the summing point. So what will happen? So let's see what are signals here. If you see, analyze this carefully, you can say this is A plus B, signal is A plus B. And the signal coming out of this is A plus B minus C. Right? So if we interchange these two summing block, what will happen? These two summing blocks are interchanged. The only thing is like a we can say it's like a commutative law. If we interchange, nothing happens, but we need to subtract or add something. Doesn't nothing change. You can see that here instead of A, let A start. Let me start with C minus. So C is coming initially. Now A minus C हो गया. Then we can add B. Both signals are added with B. So B. So this everything's remain the same. Nothing. Okay, this is like a commutative law. A plus B minus C equal to A minus C plus B. Right? Both are same. No difference. I just interchange. Nothing happens when you interchange the summing point. Now I can also split the summing point. So how am I going to split? Okay, suppose I have a summing block here with three signals. Three signals. One is plus, another is plus, another is minus. For example, this is three signals coming. Let's say this is A, this is B, this is C. This can I can simplify this using splitting this summing point into simplified two summing block, right? Taken two at a time. Two signals are coming, so I can have one summing block here, right? B signal is coming here, A signal is coming here. So both are plus plus. So here plus plus. Then I can have another summing block here, with this is signal is plus here, because here it is plus a plus and b plus. Here I have a and b are plus here, so I add plus here, and c here you can see it is minus, so c minus, right? So output in both cases, here output is a plus b plus, so b minus c, because c is only minus, a and b are plus. The same thing here, a and b are plus, so here we have a plus b, and here we have a plus b minus c, right? These are logical, but you have to use it at proper place. So it is very important that you know these things are possible. Then we will be thinking, yeah, I can do this kind of stuff. Right. Now, same thing, we can do the reverse also. We can, I don't explain, so we can do like this opposite also. We have two summing blocks, we can combine together these two summing blocks, right? Okay, so feedback we have done. So I will give you the example. You need to do this feedback right now. I'm giving you signals. We have a signal R. We have signal R. This is going to a gain G, right? And the output, say output is C. I'm just giving you some variable C. And you have feedback H. Your feedback H. The output is going to the output is going to the feedback gain H. Now we have a summing block here. We have a summing block here. This is plus to the R and minus to the H. So this is your feedback transfer function. G is the forward gain, H is the feedback gain. Now can you simplify this and tell me what is the next transfer function? I need to represent a single transfer function with input R and output C, and this you need to find here. Yes, please write. Very important thing, you have to note this thing. This is minus. This is minus. The feedback thing is going as minus, right? This will always be plus. Usually the input is always in additive mode, and for a feedback we are always subtracting, right? We are trying to guess the error, right? So this is the minus. Plus and minus, should remember here. This is the thing. Here we can have plus or minus or reverse or whatever, but based on the question you need to simplify this block diagram. So we are converting a closed loop into a open loop kind of thing, with plan model is changed. Here it was a G was the plan with a feedback loop H. Now we are combined to a single open loop system with a modified advanced plan. We need to find this transfer function. Yeah. Okay, so transfer function we already done, but you can do fast because you have to simplify it, because you need to practice it. The more you practice, then only you can do it faster. Okay, although this is not a big important part, but still this is just practicing. Okay, so here what we'll do, we have to do slight algebra only. We already done, so we need the C is going as the input here, input to the feedback loop, so we get C into H here. So here error, you can say error, what is the signal here? R minus CH, right? R minus CH. Then we can, how we will write, we need to have a function, we need to have expression C by output by input, C by R. C by R is the transfer function. C by R will be a transfer function. G minus H into G square. Let's see. Let's see. I am not able to write here, so I'll just have some space here. So let's see. This is R. So this is your input R, and this is your summing loop, plus and minus, and this is a gain G, and this is your output C, right? So now this is coming as a feedback and giving minus here. Okay, so now we can write all these things. Now here this is R minus C into H. How this is R minus CH? Because this is C and this is CH, right? And this is output is C. So we can write C equal to, now we can write C. What is C here? C equal to gain times R minus CH. This is C. Gain times R minus CH. This is gain G times R minus CH. Right? R minus CH. Now what happens? Now what is here then? This signal is, this signal will be C time is G into R minus C. There's nothing but C, G minus R minus, this is the output, into H, again into H, again into H. Okay, so we can say C equal to, so here we get C equal to G into R minus G into C into H. Then C 1 plus Hg. Then C by R. We need C by R. So we have C equal to here. So we can make C common. So C common. So C plus GCH equal to GR. So let's take C common. C common 1 plus GH. GH equal to G into R. So now we get C by R. From here, you can say C output by input equal to G divided by 1 plus GH. Okay, so this is right. So this you need, and this multiple times, you don't need to take it single time. So what happens if this is plus? That is important question. What happens if this, the feedback is plus? Here if it is plus, the summing point, if both are plus, you can say this minus will change to plus, will change in the denominator to minus in this case, right? So when the summing point have minus, you'll have plus in the denominator. When summing point has plus, you have minus in the denominator. Clear? Okay, so this thing you should be able to do without any derivation algebra like this, right? So whenever there's a feedback, you should know this is like open loop forward gain divided by 1 plus GH, and this is when summing loop is negative for the feedback gain, feedback path. If it is positive, this becomes minus. Okay, so this should be clear. This is the feedback gain, overall feedback gain of any closed loop string. Now we'll take some example. Okay, so this I will share some of the questions. You have to do this. This is signal. You can draw this question. This is summing point. The plus addition. There's a feedback also. Now this is a gain G1. Gain G1. Again there's a gain G2. And there is a summing point here again. The two signals adding plus, plus, this is also plus, and my output is C. Output is C. Okay. Now the important thing is I have a feedback after G1, that is H. Okay, and this is going to this summing point. Again, there is a node or a branch connecting from the output of my error signal to a G3 gain. G3 gain. Okay, this is going to the summing block here, right? Now the question will be in the exam, reduce the block diagram, reduce the block diagram, reduce the block diagram. So you have to reduce the block diagram and show that the same whole thing you should represent using a simple block diagram with R as input signal and a simple block diagram transfer function, output is C. So this is one you need to find. So reduce the block diagram. Now you know what are gains? We have G1 and G2, but we have nodes. Nodes are very important. Nodes are in between the signals. So you cannot directly multiply G1 into G2 here. Why? Because there is a feedback loop going. So either you need to keep the feedback loop, either this has to move here, or this has to move here or here, that you have to decide. right? So that you can right now there is no multiplication possible, right? Here also in this loop also you cannot take the feedback directly transfer because there is a loop going here. So you should say what will mean the if I simplify here, what will change in the signal input to G3 will also change, right? You cannot combine these two and make a simple block diagram. So we have to think a bit. You have to think a bit. What is the net block diagram here? So you have any lecture coming on 10:20? Okay, so you just do it as a homework. So R is the input and the plus and minus summing block, and G1 is the gain and G2 is the gain, and there is the arrows are very important. You should not think that arrows are not important. Arrows are very important. Okay, so again I'll see the arrows, the feedback loop coming here. Okay, arrows are very important. This is arrow is like this. This is arrow like this also bottom. So please see the arrows correctly. Okay, so here I got some answers, but here you should remember that we cannot do any reduction here unless we change the branching point or node point, right? Because we know if the closed loop is possible, if there is no this branch was not there. For example, if this branching was not there, then we can easily we could have easily made the feedback transfer function here. We could have simplified this into the transfer function simple, but the problem is we have this transfer function, so we cannot simplify using a closed loop transfer function we are just derived, because we need to, so we need to change this node. This guy is making the problem, so we need to move this node to a point here, maybe after this feedback thing. We need to change this node, this guy here, this guy to after the h, after the output of G1, so that we'll get everything very clear cut. We can get everything clearly. So what will be net if I change that thing? What will happen? So you can see what is signal changing here. What is signal changing here? This input is directly going to the gain G3. So if I put into the right side of the G1, what will happen? Now it has to go to the G1 gain also. It has to go to G1 gain also. So I had to reduce for that gain, right? I hope you're getting what I'm saying. If I take this to here at this point, my signal will be going through the gain G1 also, and I have to reduce for this gain in this part, top part. So one way of I can reduce is, let's see. I think you're trying. So this R is here. We'll do fast and we'll end very soon. So this is plus and this is minus, and this node I have to my idea is I need to have something like this, which I know. This I know to reduce this I know, so that this here, the guy here was going to here, I'm taking it in this side. So now the same guy has to move to the right side. So this person will go from here, right, to the G3. G3 was initially there. So right now, at least I'll put what I already have. G3 was already there, and there was another summing point with plus. This also plus, and with G2 gain is already there, and C. Right. So what I have done, I have moved this guy. There's a guy here, so I have moved this to right side of the. Why I have moved this? So that I can get this block together, so that I can use the simplification of the closed loop transfer function in this here. I can make a simple block diagram here, so that I can simplify. But what will happen? Initially, my signal going through here was not going to the G1 guy. G1 transfer function was not going. Now it is passing to the G1. It is passing to. So what I should do? I should reduce this extra gain. If I do reduce this extra gain, what I need another simplification here. I need to have a 1 by G here, 1 by G here, 1 by G, 1 by G2, right? 1 by G1, sorry, 1 by G1 here. right? I think you're getting what I'm saying, right? Because we have moved the branching point to the right, eliminate the feed so that the feedback path is free from any of these complications, right? Okay, so initially I was taking from here, so I reduced this and I have made the signal to cross to the G1. Now I'm taking the signal right side of the block. So right now what happened, now it is simplified. Right now the block diagram is simplified. Now I can combine the closed loop thing here. Now this will turn out to be, this will turn out to be what, this guy R is coming plus this, all the thing, the plus and minus thing you can, I can reduce. You can directly write like R is coming to a transfer function G1 divided by 1 plus G1H, right? This is just simplified. R is the input. Now, now we can see that the top transfer function will be G3 divided by G1, single block, G3 divided by G1, going into the top, G3 divided by G1, and bottom in G2 similarly. G2 is the same thing. Again, both are added together, plus and plus, and output is C. Now we can see what will happen here. How can I reduce this two guys? How can I reduce these two guys? These two guys are parallel. You can see output it is plus, output both are plus. So you can add them together, right? I can add them together to a single transfer function. What will be the single transfer function? G2 plus G3 by G1 or G3 by G1 plus G2. So I can say G2 plus G3 by G1. I can make a simple individual transfer function without any complications. G2 plus G2 plus G3 by G1. And this is my output C. Okay, now we have two things, right? Now we have two things in series. So what will happen? So I can combine these two because both are in series. So this can be combined together. So it's like multiplication. So we can do something like that. G1 plus divided by 1 plus G1 R1 into G2 plus G3 by G1. So the net transfer function will be multiplication of these two bottom. So overall transfer function will be like this. So overall transfer function C by R. So those two things, if I multiply, I will get G1 divided by 1 plus G1H into G2 plus G3 by G1. So if I multiply together, what will happen? G1, G2 plus G3, G1, G2 plus G3 divided by 1 plus G1H. Yeah, I think this is the transfer function. This is the transfer function. Now what we have done, we have reduced the complicated block diagram into a simple transfer function, simple block diagram. Now I'll give you one more question. I'll stop it here. You can draw it very fast, and you can do as a homework. Okay, it is not as easy, but it is a bit challenging, and you can try it because you have learned this today only. Okay, so you can draw this input R, and it is going to a summing block, plus and minus, and it is again going to another summing block with plus and minus. Let's show the arrow, it's very important. Now this is going to be gain block G1. Again it is going to be summing block plus and minus. Arrow is the, now it is going to G2. G2 again is going to G3. Again, there is a summing block, plus and plus, plus and plus, both are plus. Okay, and this is the output. This is the output. Okay, now I'll just draw the feedback loop. First, let me draw the parallel loop. After this summing block, before G2, there is a parallel G4. G4. This arrow in this direction, which is going to this summing block. G2. This is G2. Okay. Now there is a feedback loop from the output. From the output, the feedback coming H2. H2. And this output is also going to the input as well. Output is directly going to the input as well. And the output from G2 will draw in different color. The output from G2 is also to a transfer function H1. It's also going to this place also. Okay, so this completes your questions. The only thing you have to note here, the arrows are very important, right? This is R is going to this summing block again. This output of that summing block is again going next summing block with a feedback H1. This is coming to this direction. The output is also going to the another block G1, and this is going to next summing block with plus, and the feedback loop is minus. Very important, right? Again, this output is going to G2, and you have the same signal going to the G4 also, right? And here also it is going to summing block in the output. Plus, this is plus, both are plus, both are plus plus the output, right? You can say output a variable C or any variable you like. C, you can say for example output is C. Here the output is C, a variable C. Okay, so this is you can try this. I will add some more problems and share in the Google Classroom. Okay, so I think this much is sufficient, and we'll do practice something so that we'll get a feel of a transfer function. We'll go and do some reduction, we'll add something, and then we'll go for how to design a block diagram, how to design a transfer function, right? Although there was the lecture I shared last week, it was a bit higher level, but we'll take some simple examples and understand that. Okay, I think we'll stop it here. You can, any doubts you can ask, or you can put your roll number.